Hello and welcome to the lecture Recurrent Neural Network Part 1. In this lecture, we are going to introduce first the sequence modeling. Then we try to understand what do we mean by recurrent neural network, popularly known as RNN, what is basic structure and what are the different applications of it. Then we briefly discuss the different architectures of RNN. And then we discussed the different computational graphs for different RNN models. Today, we'll start another major vertical of deep learning. It's called sequence modeling. Before this, whatever we have discussed, that was in general a kind of spatial model. Just for example, image. It's a pseudo-stationary signal. So there is nowhere some temporal relationship was not present. But here in this area of deep learning, we try to model some sequential data. For example, time series data, video data, speech data, so on. So by definition, sequence modeling is a machine learning technique which analyze, interpret and predict patterns in an ordered sequential data. What do you mean by ordered sequential data? Where current elements depends on the previous elements. So for example, in a sentence, some word of a sentence may depend on the previous word. Okay, or consecutive video frames, if you say a series of video frames. Actually, these are the frames are like images only. So at a time instant t, may this video frame is depends on t minus 5 time instance and so on. So sequence modeling is a kind of modeling where we handled this sequential data, where this temporal dependency matters. Okay, so in another way to say, sequential model in CIML system designed for ordered variable length data, that maybe we don't know if there is a sentence analyzer, some textual analyzer, we don't know how many words or how many characters are involved a priori. So it's a variable length data. So text data, audio data, video data, time series data, number of this variable over the a time sequence or a temporal sequence is not known a priori. Another important thing that we will see in our course of study in sequence modeling, that what to mean by context. We initially very briefly spell out what is context is in our previous discussion, but here also we go in depth to understand that how different machine learning models, mostly the recurrent models, for example recurrent neural networks, LSTMs, transformers, this kind of sequence modeler are going to process input step by step, capture dependencies. These dependencies are mostly temporal dependencies for tasks like this, the translation, that is one language to another language, for example. Then speech recognition, stock prediction, and so many. So as a whole, sequence modeling is another era of deep learning models where these networks, this RNN LSTM transformer, are basically model the temporal dependencies and the context, other these sequential characteristics of the data. Now, why this is important? Why in our daily life this kind of modeling is very essential? Where past influence the future. So, in language modeling, what we have just said before, in a sentence, previous words shape the next word. So, some grammatical structure, some contextual structure is there for understanding language. And these contextual dependencies, or a bit more abstract, temporal dependencies. If we say one word in a particular time we are processing, these temporal dependencies, actually, if we consider, then we can say the past influence the future. Previous words shape or just drive the next word in a sentence. Same as time series analysis in our stock prediction kind of thing, weather prediction kind of. Yesterday's data affects the today's data because it somehow maintains some sort of dependency across the timeline or in a temporal dimension. Next important thing is context. You see, context means what? If I say I am sitting in a bank to write a check, or if I say I sitting in a bank of river and enjoying sunset. Now, two words, this bank and it is same spelling, but depending on the context of the sentence, these two words are completely different. This bank is a financial institute where we sit and writing the check. This bank is a river bank where we sitting and enjoying the sunset or sunrise. So these two things are different. Now this is called the context. How it is? It depends on the surrounding words in a sentence. So that surrounding words for a particular this bank actually form the context, and depending on the context we can correctly spell out what are the meaning of this bank and this bank, how to what it. Now next thing come that data is not fixed. When we analyzing data in our previous thing, very previously we know what is the dimension of the data. If image for example, it is 256 × 256. So this data, or even if it's not, we can resize it. But here this is not possible. Here in a sequential structure, many real world input are not fixed size. Sentence, audio, video, no, nothing is fixed size. On the time axis, there are different, or on a temporal dimension, they are different. Maybe we can say in a sentence, different word length is possible. In a video, the number of frame may be different. So variable length data handling is also a part of sequential modeling. Now the most important that what we said, temporal patterns So what dependency or what semantics we are modeling, that patterns only make sense over time. That means these temporal patterns, okay, that is basically. Now just imagine a boy or a girl is running in a video. Now if we see this video, then the previous pattern in a particular, for to analyze a particular image in a particular video frame, it very much depends on the previous thing, t plus 1, t plus 2, t plus and so on in this timeline, that what are the different pattern of this running video, that is important. So in this kind of data, some patterns only make sense over time, such as some trends. Now some movie is now very popular, okay, there is some seasonal kind of, in puja season there is a lot of demand of buying clothes and something like that, in different cycles of data, okay, that maybe we can say that there is a different typical, we can say, our seasonal cycles, okay, the rain in our monsoon is not same as the rainfall in the winters. So cycles of data is also, and causality. So this is very important. It is cause and the effect relations. So when these things are involved, then the temporal pattern become a very important, and how we are going to model this pattern to understand the temporal dependency, that is the basic agenda or basic goal of this sequential modeling part of deep neural network. So another point, that in general for this temporal modeling or sequential modeling, we somehow understand, we means our model understand how things evolve. Just say that there is a pattern, okay, the pattern of rainfall over time in a particular area, a particular city or state. Now this particular pattern has a, or this particular data has a typical pattern, okay, so that I understand how these rainfall things, when it is increase, when it is decrease and so on. So model understand how things evolve, and knowing this, it generalizes better for the longer sequence. Longer sequence in that sense, long time period for this data. Or even if you know in a sentence, we know how the words come. So in a longer sequence also we can put it. In new combination, non-sync timings. That means these are the what? These are the basically for testing. And it basically improve the testing performance or better generalization, and that's why it helps. Now we briefly discuss the different application of sequence modeling. The sequence modeling, generally these applications are involved where the sequential data is involved. For example, speech recognition, where we recognize some speech. Then video activity detection, that given a video can find out that what is the basic activity there. Just for example, it is very much used in surveillance, that if there is any suspicious activity among this kind of camera, then or this kind of videos, then we can try to find out. Then in kind of bioinformatics, this DNA sequence analysis, because this is a sequential data, and we try to find out some pattern for some particular disease and other things. Then another very important aspect of natural language processing, that given a text, can we translate it in another language? So for English to Hindi, Hindi to Assamese, Assamese to English, or English to Bengali, Bengali to English, and so on. Some foreign language also is possible, English to Spanish or French to English, and such. Then another important thing is music generation. Now this is a bit generative in nature, but music is also a sequential in nature. So music generation is also a part of it. Then another important sentiment classification. Here the input is maybe some text or video. Somebody is saying something, it may be a speech, or saying writing something, this may be a text. Based on this, we can try to understand the sentiment of the person concerned. That is sentiment classification. That he is happy, he is angry, he or she is angry or happy, or he or she is a very good mood, or some this kind of thing. Now another, it is NLP, typical NLP application, named entity recognition. That what is the noun, kind of proper noun, this kind of. And it is bit broad, but it's time series analysis. So many things is come under this, weather forecasting, this kind of there is some other aspect is for the predicting shared stock prediction kind of, then time series analysis. So what we understand, that the major advantage or major application areas of sequence modeling, where this sequence matter, a temporal aspect or temporal relationship matters. Now what we are first to understand, what is the machine or what is the model that is going to model this kind of sequence, and how it is different from the CNN. It is not CNN. CNN is basically used for spatial. Although we have said that image is a pseudo-stationary signal and basically a spatial modality. But that also we see in later part, that in image also we can find some sequence. That we'll see later. Okay. Now let's start with recurrent neural network. That is very well known for RNN, well known as RNN. Okay. Now RNN is this simple structure. This is one input, one node, and there is a feedback path to this node. So this is called internal state. So RNN have an internal state, and this internal state there is a feedback path. Now we'll try to understand it. RNN, this is apart from this very simple structure, as we can see this RNN, there is no output involved. But there may be a case where this output is also there. It's RNN with output. This will generate output. So output is optional, but RNN can output a vector at any time step. One thing first to understand, that we have to understand how it works. Okay, so that is the major thing to understand, how to understand this recurrent neural network. But first one question will come in our mind, why this term recurrent come? Now this recurrent thing means which call itself, and you can see here that's somewhat analogical, some sort of similarity of recurrence, that this kind of this internal state or this RNN module, just one state, is calling some sort of itself. So what does this mean? We'll see later. If we unfold this structure in time dimension, it will actually give you the ideal. So let's try to understand this. This is the RNN structure. This structure is just written more technically, this input output structure on this, and then we unfold it in time dimension. Time dimension means this x0, x1. This is x0 time instance. Sorry, this is input, but it is a 0th time instance, first time instance, second, and so on up to k minus 1. Okay, just a hypothetical. Now this is our this model. Okay, now first we have to understand what are these values. What is x? X is input, and this x, there is a weight matrix. It is wx, w for weight parameters, or it's a weight matrix x. This x is somewhat multiplied with this to go this internal state of the RNN. Another thing it is coming, that h is what? H is the some hidden state from the previous state, as we can see here will coming. So it is wh is the parameter, and this, there is a path from self, and over time it is h0, h1 and something. So it is a hidden state input from the previous state, or hidden input from the previous state, and this is the output O and the corresponding weight matrix W. This is the very basic structure. If you unfold it in a time scale or in a temporal direction, it looks like this. This is a simple structure. One it is at time instant 0. This is input to the S0, and this is the output, and this is the very initial state, and it will generate H0. H0 is the state where this H0 is actually this, so it going to the next state. So this is the one thing we have to understand, that this node, this RNN node, has two input. One is the corresponding or that current input, and another is the kind of input from the previous state. So x1, and it is, since it is coming from h0, it is coming. So s1 is a kind of function that we will define in the next slide, that basically works with two things, and this x1 is weighted with this wx matrix, and this h0 is weighted wh matrix, and then this h1 is being joined, and this h1, if it is weighted with w0, sorry, wo, to get the output, since it is time instance 1, and then next to the go to the state 2. Now you can say this is h1, it is coming from this state, and it is the current input is x2, again it is wx, and it is weighted with wx, this wh weighted with h1, then we get this h2, and this h2 is multiplied with wo to get the output, and so on in this up to k. Now one thing that we'll discuss next in details, but one thing we understand, these wx's are all same, so there is some kind of weight sharing used. Even wh are same, whatever is the input, the h, these are same, and wo is also same, so there is a weight sharing is used. Okay, so these are the basic structure of this recurrent neural network. and how this recurrent path is being understood in a time axis. These recurrent things become this. We coming back this slide frequently when to understand the different other structure. But this is the basic structure. If we understand it properly, then we can understand any concept or any complicated or any concept over and above this. So this is very important to understand. This is a very naive RLN structure. Okay. Now here you can see the what actually happening here. This is the tth time instant, the time step t. So here for understanding is that ht1 is from the previous state h, the st minus 1. This from this it is coming ht minus 1, and this particular time step, the input is xt weighted with wx. This ht minus 1, this state input is basically from previous state. This is weighted with wh and it is. Now what is ht? What is happening here? This is happening, there is some function fw here. So two input, one is xt parameterized with or multiplied with wx, another is ht minus 1 from the previous state multiplied with wh. So two input is here. So this function here in st, that is going to find ht or derive ht in this way. Okay, so this function at node st with parameter ws. Okay, this weight parameter. So what is the parameter wh and wx? So this is the state output and the time t. This is state input from the previous state from the time instant t minus 1, and this is input at the time instant t. So this is the basic formulation of a simple RNN node. So in RNN, a sequence of vectors like xt minus 2, t, x1, xt, s1, x2 is processed by applying this recurrence formula, because it is, as we said, that this recurrence thing is basically doing this structure from previous state to the next state. Okay, so here we can get this. The same parameters and same function have been used in each time steps. So that's why wh, wo, wx are same at its different node and different steps. Okay. Now here we just spell out what do we mean by this. This ht, f of wht. Now what do we use wh of ht minus 1. This is the previous state input at ht minus 1. It is multiplied with wh as is we discussed, and plus this is wx is multiplied to the xt, that is the input at this time instant t. So wx xt, to add this to put a tan h nonlinearity over it, get ht. So this ht is this, and what is yt? Yt is basically the w0 is multiplied with ht to get yt. So that is the output, if at all output is required to produce. So this essentially view a very naive RNN node structure and the mathematical formulation of a very small basic RNN node. Now we are going to understand different recurrent neural networks based on the process sequence. So what do we mean by process sequence? That what is the basic structure, that one to one or one to many or many to one, many to many, and so on. So we start with one to one, although it is not a typical sequential model because there is no sequentiality here. It is a one to one model. model will come next slide, you can understand. Some vanilla neural network is basically. Next come one to many. That means input is one and output is in general a sequence. That means multiple output. So RNN generates a sequence or many outputs after seeing one input. So what is that? Image captioning. So image is one input and captioning is basically a sequence of words or output is a sentence or multiple words, something like that. So this is the one to many. Now come many to one. Input is a sequence, output is a class level. For example, sentiment analysis. There is some video frames or some speech or some textual, some sentences. That is the input, and what is the sentiment is a single output. Video activity recognition. There is a video is basically the input is a sequence of video frames, and output is basically what the activity is. And many to many is that neural machine translation, where input is also sequence, multiple, output is also sequences and multiple input, multiple output. So neural machine translation, video summarization, this is kind of this many to many mode. Let's try to visualize it properly. Now this is the one-to-one model. You can see here, this is not typically, as we just said, not typically a sequential model. The input is one. It's a vanilla neural network. This model is one to many. So here you can see, as we said, that it is image captioning. This is one image, and this image is kind of, so it input here, and this input is propagated forwardly, forward direction. Now we get some multiple word or some sentences kind of thing. So RNN generates a sequence after seeing one input. So these are the sequence. Okay. So this is one to many. For example, this is image caption. Input is image. Now output is a sentence, multiple words, like that. Next come the many to one. Many to one is basically the sentiment analysis kind of. Many means what? This is the some text or speech sequence, and output is single because it is what kind of sentiment. It is happy or some emotional situation is that is a bad or good kind of. So what is a particular sentence? After reading a text, what is the sentiments of a person? He's become maybe angry, maybe very happy, maybe sad, or something like that. Okay, so this is important thing is that its input is this text or speech or something like that. Now output is a particular sentiment. It's many to one. Next come the many to many. That is video captioning. See that input is a video sequence and output is word sequence. So here you can see the video sequence have been given. This is a very hypothetical picture. It may be input also, but this kind of input is this, output is this. So it is the many to many kind of process sequence. Okay, and this is example is video captioning. So for each frame there is some sort of caption. Next come is another many to many. That is frame level video classification. Given a frame, what is the frame is saying? Okay. Something like that, or it may be another thing, but not exactly, but come similar. Machine translation. Given a word, what is the in a sentence and in another sentence in different language. Definitely, if there is a number of words same, this may not be same. So accordingly, this RNA will be structure, process sequence will be different. So one important thing that we have to understand that it depends on the input output characteristics, and based on these input output characteristics, RNN can be framed in a different way. And but their name structure, this is the one input, this is just a one RNN node, this is input, this is the RNN node, and there may be output, may not be output, as we have said before. Here output is there, here output is there, but again here is interestingly there is no. So this is the way we generally implement the RNN based on the applications. Okay? So that is the major understanding, that how this neural structure or recurrent neural structure are basically different based on the input output characteristics or kind of input output mappings. Okay, now we are going to discuss another representation of the recurrent neural network called the computational graph. So this is the way of representing what we have discussed earlier. What is the naive structure? Now here we can get a full picture of recurrent neural network. Now here this is the first time instant that H0 is coming from any initial values, some initial thing. This Wx is the, as we discussed before, the weight matrix for the input. S1 is the first time instant, this is the state or the RNN state, and O1 is output at this time instant, t is equal to 1. And WO is basically what? It is the weight matrix for producing output. So this H1 is basically multiplied with W, we get O1 output. Similarly, this H0 is multiplied with WH, we get this. And here in this one, we put this W0, I said H0 into WH plus X1 into WX. This summation we put a tan H or any nonlinearity as per requirement, we get H1. So this is the first node of the RNN at the first time instant. And this is very essential. If there is a sentence that I am a good boy, and this word is your granularity, that in word granularity you are thinking, so then it is I will come. Then in next thing it is like this. In the next part I, this is am. So in here is also same thing. This state 2, basically this state 2, it is 2 input from previous state H1, it is H1 multiplied with WH, and this the current input, that is X2 multiplied with WX. Then what is H2? H2 is basically the X2 multiplied with WX into H2 plus WH into H1, and then we put a non-linearity, let's say tan H. So tan H of Wx into X2 plus Wh into H1, and that will form the H2. And this H2 is multiplied with WO, get O2. So what is important to understand? You see, this is Y, this is am. Just for example, will come later when we see this neural language processing kind of, or natural language processing, how this neural architecture going to understand or implement this kind of sentence in any language, in English, Hindi, Bengali, and so on, in foreign language also, that we understand it. Now, one thing is very important to understand. This is I, this is am, then a good and boy. So this is the wordings. And there is a temporal relation. After I, am is coming. No boy is coming, it's am is coming. So this time dependency. The first instance is I is coming, second instance am is coming. So this I is somewhat trigger this am. So that contextual dependency or time level dependence, we can say, kind of, and it's not same thing, but here it is a similar kind of thing. The syntactical dependency of English language or any other language, that is being implemented by this formulation or by this architectural design, and that you have to understand. In after I, am will come. After am, a will come. So I am a. So this is something like this. So then this machine or this model is going to understand that syntactical dependency of a sentence in a particular language. And that is very important. That is why it is a sequential modeling. You can understand that this, it is, if we write I, boy, a, good, something like this, then it will not be a valid sentence. We cannot understand. So if a machine to understand and interpret the meaning of a sentence, or at least some sort of translation of the sentence, then it has to understand this contextual dependency. And this contextual dependency or syntactical dependency is coming in form of that is in temporal way. After I am, after am a, after a good, after good boy. So this simple statement, I am a good boy, or simple sentence, this is being modeled by this computational graph or this RNN structure. That we have to, this is a very hypothetical language just for understanding. It may not be the case we have always in output. That's why we put this dash line. Output may be there, output may not be there, based on the application. If there is a kind of machine translation, one text or one sentence in English to one sentence in Hindi or Spanish or German, so that may be the output is there. But if it is a kind of sentiment analysis, so this one sentence is there, some sentence, and there is only output. This output is not there. That's why output mean always there. So that's why we put dash line. But that thing we have to understand. That is why we put this computational graph. That how this syntactical dependency, lot of things we can say, which is the contextual dependency, more complicated semantic dependency, mostly in the computer vision task. So these kind of things we very much well modeled by our recurrent neural network. Okay? And we'll see for the different RNN structure, say one to many, many to one, many to many, and so on, how this computational graph differ. Okay. Now another important thing, that the weights, we have said before and we repeat here, And you can see these WH are same in the all nodes. WX are same in all nodes. WO are same. So it is a weight sharing is done there. And we have discussed what is the advantage of what weight sharing. That is substantially reduce this kind of computational cost because these weights can be reused. So this is the important aspect of computation. Next slides onwards, we try to understand what are the computational graph for different RNN like many to one, one to many to many. Now we are going to understand that this many to many recurrent neural network, what is the computational graph and how actually this is being implemented. Now as we understand, many to many means what? There is a many inputs and many outputs. Okay. So here this many input means can say some words in a sentence and it may be in the similar sentence in the other language. That may be just an example. And we have discussed this is the structure. The question comes, how this we understand that we get the proper output. Okay, so this is x1. See the training procedure in the next lecture, but here we at least try to understand what is the loss involved. So as we discussed, these weights are shared for this many to many, and this there is x1 and there is some intended output, but is it always the case we get the intended output? Definitely not, as some primary epochs, some initial epochs, it will not the same. So there is loss incurred. Now one thing is very essential to understand here, that this loss which has been incurred here, that how it is used to update or train this network. Now this loss, it is for this node, for L2 is for X2, L3 is for X3. It is from a very straightforward way. But as a whole, if you say there is a single sentence in, let's say, English, and there is a sentence in Hindi, so this is a word-wise loss, just hypothetical, and try to understand that I, so may, so there may be this I and may, so this may be a loss if it is not properly implemented or properly trained. So this is the way we are trying at different word level. For our example, we have it mixed. But in sentence level, there is an overall loss. So given this sentence, one sentence, that I am a good boy, मैं अच्छा लड़का हूँ, or something like that. Okay, so there is a word-wise loss at each step, and there is a sentence-wise loss. So one thing that will going to important here, when we going to train this kind of network, then these two type of loss we have to take. Now how these losses can be taken into consideration to train or update these parameters. Ultimately, end of the day, we have to update this parameter. It is at the very beginning we are initialized some random initialization, and then we're going to update them as per our kind of backpropagation. We'll see it is not exactly backpropagation, it will call something else called BPDD. Backpropagation through time, that we'll see in the next lecture. But this is very important to understand that this loss is kind of node wise, or for our example word wise, and this is a total loss, and that is sentence level loss. And this is input sentence, this is output sentence, and definitely some loss or some error, and that error is going to drive this node level error is there, and accumulatively when accumulate this loss get the overall loss that we have taken. Okay, next we'll see many to one. Now many to one also are very interesting. Now many to one, this h1 is there, this h1 is going to s2 only, and this h2 is go to the s3 only, s3 is going to s4, and so on, hk1 is. So one thing is possible, that if it is a very big network, so there is a lot of time instances or very big sentences, that means there may be a situation that this h1, h2, h3 may not that much effect on this escape because it is ultimate. So in some cases we see this kind of thing. This h1 is also going as output, h2 is also going, h3 is going, h4 is going, even hk minus 1 is going. Okay, so that is very important to understand. This is another very interesting observation. Now we are saying that is very kind of trivial kind of thing, but when application come and we'll go to particular application of many to one neural net implementation, we understand how it basically going to help. Okay? So this is the many to one. Then come the one to many. This is very interesting kind of thing. This is input, but one thing, this is only one input. These inputs are not there. Is there no inputs? Maybe possible, no inputs. But essential, this one case, you can say kind of implementation, that what will be this input if we try, then this is the very interesting thing. When we'll see some sort of our transformer model also, this kind of in decoder only case, this kind of. So what is the output of the previous node is going to the input to here. When we use this, that we have to predict the next word, that we have to predict the next one is some sort of that I here. This I, this what will be the output? If it is I, the next what we are going to predict. So it is am. So now am is B. If am is the output, input, then this one coming here, understand, as the input. That is very interesting. Now am is coming here, and what is the output, intended output? It's A. So I intended output am, because after I am. So if am is, then that will what is the input A. Now see one thing that is very important to understand, that when we calculate or try to predict the A after am, we are not only see the am, we see the I am, because it is coming from here. So by seeing this I and am, definitely more easy to say, oh, that will go to A. or easy to learn. Now in next, this A will come here. So I am A. So A will come. And what this will going to predict is a good. Now here you can say I am A. All these things. And this is a good. And so on. So this is a very fascinating kind of picture. That input of the previous node output of the previous node is coming the input to the next. And this will go on. Okay, so this is a very interesting kind of architecture or computational graph for one-to-many RNN architecture. Okay, we'll definitely come to discuss the very details of this kind of. We're just introducing the concept so that you can think about it. You start thinking about all this concept. So, this is summary what we have discussed in this particular lecture. We introduce sequence modeling. Then we discuss the very basic RNN structure and its application. Then we understand the different RNN architecture, process sequence models, and then we discuss the computational graphs of the different RNN models. In the next part, we'll try to understand the training of neural network. In the next part, we're going to discuss the training procedure of RNN in recurrent neural network. Thank you very much.